Every second, financial platforms and enterprise networks ingest massive streams of data. To extract value, these systems must pinpoint the peak revenue streak hidden within a volatile, year-long data set. In computer science, we call this a subarray. It is a continuous, unbroken sequence of data points located within a larger set. This data is rarely stable. Positive days build a streak's momentum, while negative days actively drag the total down. Identifying these exact boundaries within milliseconds allows high-frequency trading platforms to react to trends as they emerge. The intuitive approach is brute force. You check every possible start date against every possible end date, calculating the sum for each combination. This logic holds for a 7-day week, but scaling to millions of server logs requires an unmanageable number of calculations. This graph illustrates the breakdown. Execution times on the vertical axis explode as the problem size increases. In production, this causes user interfaces to freeze and CPUs to spike to 100% capacity. Processing millions of data points efficiently requires an algorithm that finds the peak by traversing the data exactly once, without using extra memory. Kadane solved this with a linear time approach. To understand it, we can look at an isolated array of numbers representing our data. The algorithm handles the logic using just 2 tracking variables, the active running streak and the all-time global record. We scan through the array once. As we move forward, we accumulate a running total. We take the 4, absorb a minor loss at -1, then climb through the 2 and the 1. As long as the net sum remains positive, the current subarray is worth keeping. The running total can still reach a new peak. This reduces the dataset to a localized choice at each step. You either extend your current streak or you abandon it to start fresh. When we hit the -5, the loss is significant. Our active running total drops below 0, while our record remains stored. This highlights a mathematical property of contiguous arrays. Any prefix that yields a negative net worth will only drag down future sums. The algorithm ignores the negative prefix, resets the active streak to 0, and begins the calculation fresh on the next data block. At the end of the scan, the global record variable holds the peak continuous sum found during the pass. The algorithm processes the entire array in linear time, finding the peak while using a fixed amount of memory regardless of the input size. Even an efficient, optimized algorithm requires robust edge case safeguards to remain completely stable in a live production environment. Consider an empty array. If a database query fails and returns no data, the algorithm has no values to compare. Without a fallback, the system may suffer a crash. A hard-coded safety check returns 0 immediately if the input is empty. In an all-negative dataset, where every point is a loss, the logic must identify the single element closest to 0. This ensures the system reports the least damaging period rather than a false positive. High-performance code is defined by its ability to navigate these scenarios without suffering a catastrophic failure. In quantitative finance, this algorithm identifies profitable windows within volatile stock markets in real time. Computer vision pipelines use this logic to rapidly isolate high-contrast objects from background noise by treating pixel intensities as a numerical array. In genomics, it allows systems to scan massive datasets to locate significant gene-rich DNA subsequences. These records of algorithmic history show how optimized logic expands the capabilities of modern engineering. The structure of the algorithm determines what software can achieve at scale. Kadane's algorithm demonstrates the efficiency of a civil pass scan. It discards detrimental prefixes to maintain the optimal running sum.